Hello, everyone. We're going to start with a problem that I've warned you guys about. It's sort of a bread and butter electronics type question that everybody that completes the calculus-based physics semester 2 course should be able to do. And that's being able to take a device like this that you see on your screen right now called a galvanometer and make it into an ammeter or a voltmeter. And it really is the basis of how multimeters work. Really, all that a galvanometer is basically a coil of wires around a magnet that basically the higher the current that goes or around a piece of iron and the higher the current that goes through it, the more magnetic it gets. And that actually causes the coil of wire to tilt, and that tilts the actual needle. If the current's going one way, it'll tilt one direction. If it's going the other way, it'll tilt the other direction. And it's normally just has some vague numbers on the front, like positive 30 to negative 30 on the galvanometer, or positive 50 to negative 50, or positive 100 to negative 100, positive 250, or even 25 to negative 250, or even negative 25. This one is the one I'm sort of designing by. So we're going to consider a galvanometer like this. Basically, it deflects to 30 microamps. When you actually put 30 microamps through it, it'll deflect all the way to 30. If you go one way, it'll go to negative 30, the other way to positive 30. And that's when you have it set to the 100 ohm resistance that you see down here. So basically, if you connected the high end to the red and the low voltage end to the black, and you sent 30 microamps through it, it would encounter a resistance of 100 ohms, but it would read full deflection, either positive 30 or negative 30, depending on which direction you did. So we're going to take that same voltmeter, or excuse me, galvanometer, and make it into an actual ammeter by designing it to handle a 3 amp current. So that's the problem that we're going to solve today, or this time at least, and I'm going to show you how that works. I'm going to stop sharing the screen. And there's the actual problem. A galvanometer measures 30 plus or minus 30 microamps at full deflection and has a resistance of 100 ohms. Use this galvanometer to make/design an ammeter that can measure up to 3 amps. So the big deal with a galvanometer is if you exceed the amount of current that it's allowed to handle, it just doesn't function. You might even break it. So what we have to do is figure out a way where we can allow a full 3 amps to go through a circuit, and that would actually cause a full deflection of 30 microamps. So the way we do this is we create what's called a shunt resistance. So we're creating an ammeter. So our ammeter, which I'll just represent as a box like this. So this is our ammeter, and basically what you expect is 3.00 amps to be going in. So this would be the red side, if you actually made it into an ammeter. And then out the black side, we would have, of course, 3.00 amps going in. Now the problem is we can't send 3 amps through the galvanometer, because that would actually cause it to either break or just peg out and possibly malfunction. But either way, you're not going to get a good measurement. So what we really want to do is we want to take this current and break it into two. We're going to send it through this resistance right here, and that will be called R sub S, and that means shunt. It's a shunt resistance. So we're going to use a shunt resistance to actually make this galvanometer into an ammeter. Now, what we have to do is we have to take that full 3 amps and take whatever the ammeter can't take and send it through here. And then whatever the ammeter can take, it'll go up through the actual galvanometer, which will represent as a box with a G on it, followed by its actual internal resistance, which is 100 ohms. And it'll come back like this. So when it is actually 3 amps, what we want is 30 microamps to go through there. And then we want the rest to go through here. The rest would be 2,999,970 microamps. That's what you want to go through there. Now, obviously, that's micro, so if you move the decimal 1, 2, 3, 4, 5, 6, you see that's just under 3 amps. So the vast majority of the current is going to have to go through here, and a small part will go through here. As you can tell, this resistance is kind of low. It's 100 ohms, and we've actually got to get way lower than that to make basically 200 or 2.99 amps go through here. So that's the way parallel resistors work, is basically the largest part of the current goes through the lightest resistance. Now, since it is in parallel, we do have some information that can help us. We know that the voltage across the galvanometer, which is really from here to here, in other words, it includes the 100 ohm resistor, has got to equal the voltage across the shunt resistance. So I'll write that as Vs. So this voltage right here, which is shunt resistance, is equal to the voltage across there. Now the voltage in the galvanometer is I galvanometer times 100 ohms, just from Ohm's law, V equals IR. Similarly, the voltage in the shunt resistance is the current through the shunt resistance times the R shunt. So really our design project here is really just specifying what the shunt resistance must be in order to allow 30 microamps to go through the galvanometer when a full 3 amps goes into the new designed ammeter. So our job is to figure out that. Well, we already know what the currents are. I've worked those out. So I just got to put them in there in amps and solve for the shunt resistance. So I'm going to say 30 times 10 to the negative 6 amps times 100 ohms is equal to 2.999970 amps times our shunt. And that gives us our shunt should be 1 point, now this is kind of funny, but I'm going to write it all on there anyways, 1.00001 times 10 to the negative 9th ohms. So basically all we did was we divide 30 times 10 to the negative 6 by 2.999970, and that gave us 1.00001 times 10 to the negative 11th. Then we multiply that by 100 and got 10 to the negative 9th instead. So that's what our shunt resistance is. We literally have to have something slightly bigger than a nano ohm over here. Obviously, that's a challenge. In principle, you could just put a bank of 1 ohm resistors all in parallel, on the order of billions of them maybe, and make a resistance that's smaller. But obviously that's kind of crazy. But there are ways to make small resistances. Ideally, you wouldn't want to drive 3 amps through a 100 ohm galvanometer. You'd want to switch, like that galvanometer that we showed had a chance for you to use 2.4K. That would obviously make it a lot easier to design an ammeter out of it. But with this, we will actually have a properly designed ammeter. So the ammeter now is basically this galvanometer with the internal resistance of 100 ohms in parallel with a shunt resistance of approximately 1 times 10 to the negative 9th ohms. And what happens is when 3.00 amps goes through there, we get 3.00 amps coming out, and the galvanometer shows a reading of 30. Okay, if it's going to the left, maybe it'll show negative 30. If it's going to the right, it'll show positive 30. So what we now know is that obviously 30 compares to, or is to be read as 3 amps. Now the big thing is, how did we screwed up the schedule, this actual scale? Is it really linear? I mean, if I cut this 30 in half and say go to 15, is that really half of 3 amps, which would be 1.5? Well, to see that, we can just see what the actual galvanometer current is. So the galvanometer current, Ig, is actually going to be equal to, from this equation right here, the galvanometer current will be, I should have been looking at that a little better, sorry. The galvanometer current will be equal to basically the shunt resistance times the, are divided by the 100 ohms. So that's 1 times 10 to the negative 9th ohms approximately over 100 ohms times the current through the shunt resistance. So we see that whatever current comes in is always going to add to the actual shunt resistance. Uh, Basically, the shunt resistance plus the galvanometer current, or the shunt current plus the galvanometer current, will add to give you the total current coming in. And we see that the galvanometer is actually reading something that's proportional to the current going through the shunt. So it is a linear scale. So that does mean we can, say that 15 is equivalent to 1.5. 7.5 is equivalent to 0.75 amps and stuff like that. So that's basically how you make an ammeter out of a galvanometer. I hope that helps.